El jueves 8 de mayo de 2025, la Red Iberoamericana para el Avance de la Ingeniería de Software Cuántico, RIPAISC, y el grupo de computación cuántica del Centro Latinoamericano de Estudios en Informática organizaron una reunión, charla, webinario online con ingenieros y especialistas de la compañía SpinQ para conocer algunos de sus dispositivos y permitirnos una ronda de preguntas con sus ingenieros. A continuación, la grabación de esa sesión.
And I'll make a short introduction. So, welcome everyone to this online meeting, webinar, workshop, where we have engineers and people from SpinQ, the company that builds several of the SpinQ quantum computers that we've seen around. We have this meeting is organized by the RIPAISC network, a Latin American network that tries to foster quantum software engineering, and also by the Center for Latin American Center for Studies in Informatics. And this meeting is made possible because a contact that Victor Macarrain made. Victor Macarrain, that is now online, is the owner of the first quantum computer in Argentina, SpinQ 2 qubits, that he'll tell us about. So, and from China, we've got Rachel. I got Rachel's name. I don't know the name of the other people. So now Rachel will introduce herself and the rest of the SpinQ team. I will give the microphone to you, Rachel, now.
Okay, thank you, Professor Fernandez. And first of all, thanks for your inviting. And I'm Rachel, the sales who has been in touch with Peter before. Yeah. And today, there are 3 engineers who are participating in this meeting remotely. They are respectively in charge of product support, Mr. Wu, and hardware engineer, Mr. Lin, and the software engineer, Mr. Yu.
Hello, everyone.
Hello. Okay, and yeah, and first I will have a brief introduction about our products, and after my presentation, we will discuss the questions you may have. And yeah, and I understand you have quite a few questions about our products, so I will go through my presentation quickly, and we can save more time to discuss the questions. Is that okay? Okay, now I will share my screen. Okay, great. Okay, let me introduce our company first. And SpinQ is a company that provides one-stop solution in quantum computing, which is related to making superconducting quantum computer, quantum chips, desktop NMR quantum computer, hard platform, air provision, and software, and so on. And today, we will focus on our desktop NMR quantum computer. Yeah, and this device, I understand that some of you may have touched this machine and do experiment on our Gemini Mini. So I will have a quick introduction about this device. The Gemini Mini is the portable device, and it has 2 qubits real quantum computing system and 8 qubit simulator. And as you can see, we can do all operation on the screen. And we also can observe the hardware on the top. Besides that, Gemini Mini also offer content courses and exercise for the beginners. And this is the interface about the Gemini Mini. The software includes 7 parts, including real quantum computing, simulation, training, and quantum course, and so on. And if we click on real quantum computing, we will go to this interface, and we can in this interface we can drag the quantum circuits to do experiment, or we also can choose the algorithm we put in the device. For example, if we choose the global algorithm, the circuits will be built accordingly. And if we click run button and wait for about 30 seconds, the results will be shown accordingly. And here is the brief introduction about the Gemini Mini. I will play it. Thank you.
Gemini Mini.
How about now?
Perfect.
Gemini Mini is a 2-qubit portable quantum computer. The whole machine weighs only 14 kilograms and works at a room temperature of 0 to 30 degrees centigrade. Gemini Mini has a touch screen for interaction. The touch screen can be rotated approximately to 80 degrees, which is convenient for observation and operation from different angles. On the top of Gemini Mini, there is a window used to observe the inside of the machine. Pull out the shutter. Then the structure inside the instrument can be observed from above. All operations on the Gemini Mini are done on the touch screen, where we can perform 2-qubit real quantum computing or make simulations up to 8 qubit. In addition, there is a built-in quantum course in the Gemini Mini software, and according to the course, the Gemini Mini gives corresponding exercise training for learning and teaching. Real quantum computing. Gemini Mini can perform both single qubit and double qubit experiments. In the experiment interface, we have defined some quantum gates for the system. You can click about gates above to get the information about these quantum gates. To create an experimental circuit, users can directly drag the quantum gate to the lines. The quantum circuit can be slid. Each quantum circuit can add up to 60 gates. To delete gates on the quantum circuit, we can drag the gate on the quantum circuit to the red area at the bottom to remove it, or click clear at the top to clear all quantum gates at once. Before running an experiment, click Untitled Task to name the current experiment if necessary. After building the quantum circuit, click Run, then the machine will start the experiment, and the progress bar at the bottom will show the progress of the experiment. Click Current Experiment to see the relevant information about the experiment. Each experiment will take about 25 seconds. After the experiment is completed, the results will be displayed on this interface. There is a case button on the right of the experiment interface. Some typical quantum algorithms are built into the system as examples. We can run these experiments and use them for learning.
Okay, please wait a moment. We need to adjust the microphone. It's okay. We'll go on. Yeah, we will go ahead. Okay, as I mentioned, Gemini Mini offers content courses on the device. And here is the catalog about the content courses. Then here are some screen snaps for the courses. Yeah, and I have seen the questions Victor sent me before, and I think our other models, Gemini Lab may more suitable for your purpose. So I would like to take this opportunity to have a brief introduction about our Gemini Lab. And Gemini Lab has 3 qubits and it has 2 qubits and 3 qubits available. And it offers first-step quantum computing experiment and visualize quantum experimental results. It also supports to replace the chemical sample according to your experiment. And it also suitable for education and research purpose. And here is the main interface about our Gemini Lab. There are 4 parts in the interface, and above is the knowledge. Is the knowledge of introduction and the manual about the experiment below. And this is the equipment interface. We can check the temperature and the magnetic field strength and so on in this part. And about the first module, there are 9 contents. It contains 9 experiments. And the users can learn the physical behind quantum computing step by step. The second part is quantum algorithm. By performing experiment, the users can learn how to apply quantum algorithm to solve specific programs. And the second part is integrated quantum technology. It is including quantum control technologies. And the first part provides an open experimental platform. And it also provides the user with high degree of freedom to conduct their experiment. Here are some typical layer experiments. For example, the rapid oscillations, quantum gate, and so on. And here is the quantum control parameter construction. And here is the quantum circuit layer experiment. Besides that, Gemini Lab also offer comprehensive teaching resources. Each experiment covers the manual and the introduction about the experiment. And the SpinQ device works with the quantum programming SpinQ, which is developed by our team. It is compatible with the IBM's RIPAISC. And here are some open resources we put on GitHub about SpinQ. Okay, here are the presentation And do you have any questions about the product?
So thank you, Rachel. It was very clear presentation. I think that the product that you show in the last presentation is the one that you have in front of you. Is that right? Is the lab product the one that you have in front of you in the table?
Yeah. This is the Gemini Lab. Is the quantum computing experimental platform. Yeah, it's the second product I introduced in the presentation.
Excellent. So for people here in the conference, we'll do as follows. Raise your hands so we don't speak on top of each other, and I will try to organize the questions. Meanwhile, I will start with a question myself. Rachel, the products that you introduced are mainly educational products. So how does SpinQ imagine the use of these products in educational setting? Is one, for example, what is the main difference between the first product you show, the 2-qubit quantum computer, versus the SpinQ lab?
Meaning和直观到的区别。第一个，我们先说什么是 meaning。Yeah. Hi, Professor Fernandez. Yeah, the first product Rachel showed in the presentation is that the Gemini Mini, right? Yeah, the portable one. Oh, yeah, thank you. Actually, that's a portable quantum computer. It also has 2 qubit as a Gemini Lab, but the difference is Gemini Lab is an experimental platform. And yeah, you can see it can be open, and the sample can be replaced from here. It will also, we can use a magnet. A magnet to act here, and you see the field, the magnet field will change, and it will affect the outcome of the experiment. Yeah. Generally speaking, the Gemini Lab, this platform, is much more powerful than Gemini Mini. For Gemini Mini, is mainly for teaching in undergraduate, for high school students or undergraduate, but Gemini Lab, it can be used by undergraduate, a master's degree students, a doctor, to learn quantum information, informatics, quantum computing, and to do some entry-level experiments. Yeah, as you have learned before in the presentation. Thank you.
Yeah, I have something to add, Rachel. Let me explain that. I'm Lin Zidong. I'm from the R&D department of SpinQ, and the essential difference between the first product and the Gemini Lab is the Gemini Mini. The first product is an integrated quantum computer, which means the users can, the main function of the product is user enter the information and do experiment in the quantum circuits. And many of the operation is integrated. But the Gemini Lab is an open experimental platform that can allow the users to take part in all the button level operation of this whole process of the quantum computing. So that's the main difference between these two products. The first one is an integrated quantum computer. The main function is quantum circuit, but the second one, Gemini Lab, is an experimental platform, so users can use it for educational experiment or research experiment, and users can take part in every step of the button level operation in the quantum computing.
Thank you. That was very clear. Thank you. So we have some questions. Diego, you're first.
Hey, thank you very much. My question is a little more general about the. I have two questions. First is what is the principle for works, how it works, because I know this is a sample molecule, and well, more or less how you implement the qubits and so on. And I have another question about the company, and this is because you have clone services, and then you have another kind of device, how many qubits it have, and well, if there are a possibility of get access of that devices for research, because I am professor at the University of La Plata and I research at CONICET, and maybe for us could be interesting get access for that device. Well, this is my too long question, sorry.
Okay, let me repeat the question to make sure
The first is general about the company, because you have clone access to devices, and what if you can tell me about the what kind of devices the public have can access. This is superconductor qubits, how many qubits, and what kind of device. And the other is for this device Gemini that you presented. But this is the first question. Let's go to there, and then I met again the other. If you
Okay. We provide two kinds of quantum computers. One is the superconducting computer, and the other one is NMR, or so-called spin magnetic resonant computer used for education. The superconducting computer can be used for industrial use, for industrial purpose or research purpose. And now we have up to 20 qubits chips in superconducting quantum computer, and about 3 months later we will link the 20 qubit chips online, so you can use the cloud service about the superconducting quantum qubit this year. And for the NMR device, it's mainly for education purpose. So it's only up to 3 qubits. And for the device named Gemini Lab, we can change the sample from 1 spin to 3 spin, three type of standard sample. You can use in different. You can use 3 type of standard sample to meet different experimental needs. And also you can use the Gemini Lab for some research project, but the qubit number is limited.
Okay, nice. For the 20 qubit devices, there are possibility for research programs, because as a professor at the university, we have so many research project in order to run on QPUs, and then we are interested on that. You know, if the company at this moment have some this kind of programs?
I think it is depend on if 3 qubit is enough for the professor.
No, I guess the 3 qubits, at least for the research now we are doing here, is not enough, because we are trying to do many techniques that we need more qubits. That's why I made a question about this 20 qubit clone service machine.
Okay.
Or maybe if you don't have information now, maybe you can send me by email, or maybe we can talk later. There's no problem.
Yes. As for our superconducting quantum computer, now we have 20 qubits available, and we are open to access to our cloud platform this up to 3 months later.
Okay.
You could kindly share your you could kindly share your project by email, and we can see if the superconducting quantum computer is suitable to solve your problems.
Okay. Well, I will let stay for another question, and maybe if there are not anymore, I will return to make another one. Okay, thank you so much.
Oh, you're welcome.
Thank you, Diego. Jose Manuel.
Hi. Thank you for the very interesting presentation. I am a professor and a researcher at the University of Extremadura in Spain, and we work mainly on software. So I have some question about the software and how can I run circuits on your products. So I have to program the circuit using the interface you show, or can I send my circuit some other ways? And so that first. So how can I run circuits? Is there any API or something to run circuits?
Yeah, we have a Python code key, means SpinQ, named SpinQ, and you can use Python to create your program, your circuit, and set the circuit to the equipment, and the equipment receive your message and running the quantum circuit and give you a feedback in the Python program.
Okay, thank you. And then if I can ask a follow-up question, can I have some control or can I have access to the software that is running the circuit? So can I look at the transpiler or the scheduling or the task, how it's managed inside the device, or is that is closed? So more clearly, could I write my own transpiler so I can convert the circuit into whatever is running the device?
Sorry, what's your meaning of transpiler?
So if I have a circuit right on Python, so I have some gates, but then I guess that it needs to be adapted to physical orders to the device. So there is a process of compiling or transpiling going on there. So I was just wondering if it's something that we can play with, that we can try to optimize the transpiler or things like that.
Oh, the users have to use the SpinKit, which is a language or library of the based on the Python, or you can use the Qiskit or yeah.
Just to clarify the question about Juan Manuel, when you use Qiskit in the Gemini, you can set which kind of transpiler are you going to use the optimization. There are some options. I think the question from Jose, if we can configure manually this option.
Oh, okay. Let me talk with 子栋。子栋他可能说的是，他用了 Qiskit 的那个代码之后，能不能直接转换成我们的那个 SpinQ 那个内容，还是说需要什么中间的一个步骤啊？
可以。喂，听到吗？
听到。
可以。
是可以转换成，就是使用那个我们的 SpinQ 转换一下的，就是这样。我们 SpinQ 提供了一个那个 Qiskit 的接口。
就是说他如果用 Qiskit 写了一段代码之后，通过这个接口直接可以用在那个 SpinQ 上面，是吧？
对，我可以提供相关的一些地址，但是我需要它开放一下那个聊天那个输入的那功能。
哦。Hi, Alejandro. Could you open the chat window? And our software engineer want to share a link for you to have a look at our SpinQ functions.
Okay, so I think it's open, but I will check because someone already sent a message there. Let me.
它已经开了，那已经有人发过一条信息，请去那边能发吗
I can't type everything.
Okay. I will make everyone a I will make you a presenter. Who else?
I'm SpinQ.
You. Now you're a presenter. Now you should be able to write. Check again.
Okay, thank you.
It doesn't work.
It doesn't work.
Yeah.
Maybe we can share you the link after the meeting.
Yeah, do that.
I think I already found it, so thank you. I put it on the chat, so I can see there that there is some option to compile. So thank you very much.
Okay, let's go ahead.
Thank you.
Okay, so do we have any more questions? There are a few questions on the chat window. I think some of them already were answered. About the SDK, for example, we now have the link to the SpinQ. What else do they ask? They are asking whether you do any error correction. I guess not in the small computers, but will you do well? Are you doing are you thinking about any error correction or error mitigation protocols for your products?
An quantum error correction is a big problem in the engineering. So for now, in our product, we don't have logic qubit, which means we don't use any error correction in our physical qubit. So when I say the 20 qubit or 3 qubit, 2 qubit, it is the physical qubit.
Yeah,
it's not the logical qubit.
Yeah. Do we have any other questions? Anyone wants to make a question? Diego, do you have any more questions?
Yes, I like to know more or less what is the general function or what is the physical principle in what this MER works. This more or less what kind of molecule you are using, what are the where in which kind of level or band of level are implemented the qubits and but the 2 qubits. If you can give a little more detail about it.
Yes. Actually, we have some document, and for example, the experimental handbook of the Gemini lab. You can learn a lot of the under-level principle about spin magnetic resonance quantum computing from the handbook. Maybe we can share some document with you after the meeting.
Now, it could be great because as physicists, the first thing I thought is, okay, if you are implementing some qubits, all the people have the image of the dilute refrigerators, and then okay, this works at room temperature, and this is fine, but this could be fine, but how it works, this is the question.
It's not that simple, but I can give a brief introduction. The basic principle is when you put a spin a spin with a spin number 1/2 in a magnetic field, the spin will have a phenomenon called Zeeman splitting. Then it will have 2 energy levels, and we use the ground level as to represent the 0, and we use the excited energy level to represent the information 1. So this is the basic principle of the spin qubit. We know that there are many different roadmaps of the quantum computing, and most of them is using the spin qubit, using the natural spin or artificial spin. That's the only difference. So the content in our experimental handbook is very general using, and when you want to control the qubit, you use an radio frequency pulse. And when the energy of the RF pulse equals to the energy difference between the 2 levels, and the spin will absorb the energy of the RF pulse, and a transition of the energy level occur in this system. And so you can use this principle to control the qubit from 0 to 1 or 1 to 0. Actually, you can use you can control the qubit to do any rotation operation. So based on this theory, you can do any single qubit gates or multi-qubit gates, whatever you want. And about the reading out of the qubit, in NMR, you read the FID, which is the free induction decay signal. It's an electronic signal, and we sample this signal from a coil, and we can do analysis in our classical computers which is a measure and control system of the qubits. So we can read the information out. Yeah, and for more detailed information, we can share some document with you after the meeting.
Okay, yeah, could be nice if you can send me some document with more details about the molecule, what is the magnetic field, and so on. Well, thank you very much for your response.
Sure.
So thank you, Diego and Lynn, for the nice discussion. Nicolas, would you like to make a question?
Hi. Yeah. First of all, thank you guys for the presentations. It was very nice. My question was related to the last one by Diego, and I understand going into the details of the inner workings of the computer right now is kind of difficult. But I was wondering, maybe the research team for the company has some, say, published papers or something on experimental data on the qubits you have, either on the mini lab or on the 20 superconducting qubit devices that you have in the place. So if you have maybe some list of reference of published papers or something that we can read, so I think it's going to be easier if we go just read this.
Oh yes, we have two essays about our product, one for the Gemini, one for the Triangular, and we also have some essay which is cooperated with some university in China, and one of the one of the essay just be published on the PRL, so we can share all of them to you after the meeting.
Oh, that would be fantastic. So in principle, that's it. As a physicist myself, I'm more interested in how the thing works than actually using it. So if we can have access to these papers, that would be very, very nice. Thank you. Thank you very much.
Yeah, no problem.
Okay, so thanks, Nico, for the question. We have now 1 hour of meeting, and in China it's late. It's about, I guess it's about 9 in the evening. So I guess what we could do is we can free you from the meeting. We are very grateful. We are very, very grateful for your presentation, and maybe in the future we will invite you again so we can discuss and maybe tell you what we are doing with your technology. And for the rest of the people here, Victor has some spare time to show us the machine he has. So we can even ask Victor some questions, and maybe we can break Victor's machine online. Okay, so Rachel, Ling, thank you very much for being with us, and have a nice evening.
Yeah, you're welcome.
Thank you, Professor. Diego, Jose. Bye.
Bye.
Thank you for your time.
Thank you. Bye.
Bye. Thank you.
Bye-bye.
Bye.